Lightning is not just a flash in the sky. Lightning is an extreme electrical discharge, powerful enough to heat air to temperatures hotter than the surface of the sun and release enormous energy in a fraction of a second. What looks like a single bright bolt is actually the final step of a complex physical process that has been building silently inside a storm cloud for minutes, or even longer. The first key thing to understand is this: lightning is not random. It does not strike by chance. Every lightning bolt is the result of fundamental physical laws governing electricity, charge separation, and electric fields in the atmosphere. A thunderstorm cloud behaves like a massive natural battery, slowly storing electrical energy until the air can no longer resist it. If you like similar educational videos, please like, subscribe, and share the video with your friends. Under normal conditions, air is an excellent insulator. Electric current cannot flow through it easily. During a thunderstorm, however, this changes dramatically. Inside the cloud, billions of tiny water droplets, ice crystals, and hailstones are moving violently within strong updrafts and downdrafts. These particles constantly collide with one another, and during these collisions, electrical charges are transferred. As a result, the cloud becomes electrically organized. The upper part of the cloud usually accumulates a positive charge, while the lower part becomes negatively charged. The ground below the cloud responds to this imbalance. Negative charge in the cloud repels electrons in the Earth's surface, leaving the ground beneath the storm with a strong positive charge. Between the cloud and the ground, a powerful electric field begins to grow. At this stage, lightning still does not occur. Even with enormous voltage, often hundreds of millions of volts, the air is still resisting the flow of current. For lightning to happen, the air itself must change. It must become ionized, meaning its molecules are stripped of electrons and turned into a conductive path. This process begins invisibly. From the cloud, a faint branching electrical channel called a stepped leader starts moving downward toward the ground in short, discrete steps. Each step partially ionizes the air, weakening its insulating properties and searching for the easiest path forward. This leader is not bright and is usually invisible to the human eye. At the same time, objects on the ground, trees, buildings, poles, even the surface of the Earth itself, begin to launch upward-moving electrical discharges. These upward streamers rise to meet the descending leader. When one of them connects, a continuous conductive channel is formed between cloud and ground. Only then does the event we recognize as lightning occur. A massive surge of electrical current races through the channel, releasing intense light and heat. This bright flash is not the beginning of lightning, it is the final release of energy along a path that was prepared in advance. What appears to be a single bolt is actually the result of a rapid, multi-stage interaction between cloud and ground, governed entirely by physics. For lightning to exist, a thunderstorm cloud must first become an active electrical system. A storm cloud is not a passive mass of vapor. It is a highly dynamic environment filled with violent air currents, rapid temperature changes, and constant particle collisions. These internal processes are what allow electrical charge to build up to extreme levels. A mature thunderstorm cloud, known as a cumulonimbus, has a strong vertical structure. Warm, moist air rises rapidly from the surface, sometimes at speeds exceeding 20-30 meters per second. At the same time, colder air sinks downward. These opposing airflows create intense turbulence inside the cloud, where water droplets, ice crystals, and hailstones constantly collide. The key factor is that these particles are not all the same. Some are tiny, light ice crystals. Others are larger, heavier pieces of ice or graupel, soft, hail-like particles coated with liquid water. When these particles collide under the right temperature conditions, electrons are transferred from one particle to another. The physics of this process is complex, but the outcome is consistent. Lighter ice crystals tend to lose electrons and become positively charged. Heavier graupel particles tend to gain electrons and become negatively charged. Air currents then separate them. Updrafts carry the lighter, positively charged ice crystals toward the top of the cloud, while gravity and downdrafts pull the heavier, negatively charged particles toward the lower regions. Over time, This creates a large-scale separation of charge within a single cloud. The top becomes strongly positive. The bottom becomes strongly negative. This separation is not weak or temporary. It can persist and intensify for many minutes as collisions continue. The cloud effectively turns into a giant natural capacitor, storing electrical energy. As this charge separation grows, so does the electric field. The field is strongest between the lower part of the cloud and the ground below. The negatively charged cloud base pushes electrons away from the surface of the Earth, leaving behind a region of induced positive charge at ground level. Even though the Earth remains electrically neutral overall, this local rearrangement is enough to create a powerful electric field spanning kilometers of air. At this stage, the voltage difference between cloud and ground can reach hundreds of millions of volts. Yet lightning still does not immediately strike. The reason is simple. Air is still resisting the flow of current. Even an enormous electric field must overcome the insulating strength of air before a discharge can occur. As the electric field intensifies, it begins to distort the molecules of the air itself. Electrons are pulled away from atoms, creating ions and free electrons. This process, ionization, does not happen everywhere at once. It starts in small regions where the electric field is strongest, typically near the base of the cloud or around sharp objects and irregularities. These localized regions of ionized air form the first weak conductive paths. They are unstable and short-lived, but once they appear, the system is close to breakdown. The cloud-ground system has reached a critical state where any small fluctuation can trigger a runaway process. When conditions are just right, one of these conductive regions grows rapidly and organizes into a descending stepped leader. From that point forward, the process becomes self-sustaining and almost impossible to stop. Once a conductive channel has formed between the cloud and the ground, the system is ready for release. At this moment, the electrical circuit is effectively complete, and the result is one of the most violent natural electrical events on Earth. This is when lightning truly happens. The visible lightning bolt corresponds to what is called the return stroke. Despite how it looks, this powerful surge of electricity actually travels from the ground upward toward the cloud, racing along the ionized channel that was prepared by the stepped leader. The speed of this current is enormous, approaching a significant fraction of the speed of light. The electrical current involved is extreme. A single lightning stroke can carry tens of thousands of amperes, far more than any man-made power system can safely handle. This current flows through a channel only a few centimeters wide, concentrating an immense amount of energy into a very small volume of air. As the current passes, the temperature inside the lightning channel rises almost instantly to around 30,000 degrees Celsius. This is hotter than the surface of the sun. At these temperatures, air no longer behaves like a normal gas. Molecules are ripped apart, electrons are stripped away, and the air becomes plasma, an electrically conductive state of matter rarely found naturally near Earth's surface. This heating happens so fast that the surrounding air has no time to move out of the way. Instead, it expands violently. The rapid expansion creates a shock wave, similar to a small explosion, pushing outward from the lightning channel in all directions. This shock wave is what we hear as thunder. Thunder is not the sound of electricity itself. It is the sound of air exploding outward due to extreme, instantaneous heating. Close to a lightning strike, thunder can sound like a sharp crack or bang. Farther away, the shock wave spreads out, reflects off terrain and cloud layers, and arrives as a long, rolling rumble. The delay between seeing lightning and hearing thunder exists because light travels far faster than sound. Light reaches your eyes almost instantly, while sound travels through air at about 340 meters per second. By counting the seconds between the flash and the thunder, you can estimate how far away the lightning strike occurred. Another important detail: what we perceive as a single lightning bolt is often not a single discharge. After the first return stroke, the ionized channel can remain conductive for a brief time. If excess charge still exists in the cloud, additional return strokes can follow the same path. This is why lightning often appears to flicker or pulse, even though it strikes the same location. Each of these repeated strokes reheats the air, reinforces the shock waves, and contributes to the complex sound pattern of thunder. The entire sequence may last only a fraction of a second, but it contains multiple powerful energy releases. Not all lightning discharges connect cloud and ground. In fact, most lightning occurs within clouds or between clouds, redistributing electrical charge without ever touching the surface. These flashes can be just as energetic, even if they pose less direct danger to people. When most people think of lightning, they imagine a single bright bolt striking the ground. In reality, this is only one of several forms lightning can take, and it is not even the most common. Lightning is a family of electrical discharges, each shaped by the structure of the storm and the distribution of electrical charge. The most frequent type is intra-cloud lightning. In these discharges, electrical current flows between regions of opposite charge inside the same storm cloud. From the ground, this often looks like the entire cloud flashing or glowing. These events release enormous energy and play a crucial role in balancing the cloud's internal electrical system, even though they never reach the ground. Another type is cloud-to-cloud lightning, where the discharge jumps between separate storm clouds. These flashes can stretch for tens of kilometers, forming long horizontal branches across the sky. They reveal how large and interconnected storm systems can become on an electrical level. The most dangerous type for humans is cloud-to-ground lightning. Even within this category, there are important differences. Most cloud-to-ground strikes carry a negative charge, but a smaller fraction are positive lightning strikes. These originate from the upper parts of a storm cloud and carry significantly more energy. They can strike far away from the storm's core, sometimes under clear skies, and are responsible for many of the most destructive lightning-related injuries, deaths, and fires. A common misconception is that lightning always strikes the tallest object. In reality, lightning strikes wherever the electric field becomes strongest and the air breaks down most easily. Height matters, but so do shape, sharp edges, local humidity, ground conductivity, and momentary fluctuations in the electric field. This is why lightning can strike open fields, beaches, or isolated trees, while nearby taller structures remain untouched. Because lightning cannot be prevented, the goal of protection is control, not avoidance. This is where lightning protection systems come into play. A lightning rod does not attract lightning in a magical way. Instead, it provides a preferred, low-resistance path for electrical discharge. By concentrating the electric field at a known point and safely conducting the current into the ground, it prevents lightning from choosing a destructive path through buildings, wiring, or plumbing. Without such a path, lightning will still discharge, but it will do so unpredictably, often through roofs, walls, electrical systems, or metal structures. Lightning protection systems are designed to handle massive currents and dissipate energy safely into the earth, minimizing damage. The danger of lightning extends beyond direct strikes. Ground currents, side flashes, and induced electrical surges can cause injury or damage even without a direct hit. After a strike, electrical energy spreads through the ground and nearby conductive materials. A person can be injured simply by standing nearby or touching an object connected to the strike area. From a physical perspective, lightning is a natural balancing mechanism. It allows the atmosphere to release accumulated electrical energy and restore stability within storm systems. Without lightning, electrical charge would continue to build to unsustainable levels. Lightning is both beautiful and deadly. In a single moment, it combines extreme voltage, massive current, intense heat, brilliant light, and explosive force. Humans cannot control it, but by understanding how it works, we can predict risk, reduce danger, and respect its power. Lightning is not chaos. It is physics operating at its absolute limits.